Welcome to checking for convergence using the direct comparison test. So the idea here is if we are trying to find, we're trying to determine if the integral from a to infinity of f of x dx converges. It is useful to compare f to, or to find a function that we can compare f to that we fully understand. So it is useful to compare f to a function g that we already understand. And so the most useful ones to do the comparisons for are 1 over x to the p. So in particular, we can compare to 1 over x to the p, since we already have our rules for when those converge or diverge. So the official test says that if f and g are continuous on the interval from a to infinity, a is included, and if 0 is less than or equal to f of x is less than or equal to g of x. So in other words, f is trapped below g. Then if the integral from a to infinity of g of x dx converges, then so does the integral from a to infinity of f of x dx. So in terms of pictures, essentially what we have going on here is we have some function that we know, g of x, and then trapped beneath that is our function f of x. Since f of x is trapped inside, it would make sense that its integral should be smaller than the one under g of x. And so if the g of x integral is finite, it would make sense for f of x to also be finite, right? So essentially what we have here is that the area under f of x is part of the finite area under g of x. Similarly, we can do a similar trick for divergence. So on another note, if f and g are continuous, if f and g are continuous on a to infinity, a is included, and if 0 is less than or equal to g of x is less than or equal to f of x, then if the integral from a to infinity of g of x dx diverges, then so does the integral from a to infinity of f of x dx. Essentially, in this case, what we get is that the infinite area under G is part of the area under F. And so that would make the area under F also infinite. So let's just do a couple quick examples. For our first example, let's verify whether the integral converges or diverges if the integral is the definite integral from 1 to infinity of e to the negative x squared dx. So note that e to the negative x squared, or the integral of e to the negative x squared, is not one we know. And so it's not one that we can simply evaluate without using a computer, but we can do a test. So, however, e to the negative x squared goes to 0 much faster than 1 over x squared. And so what we wind up getting is on the interval from 1 to infinity, we actually have that 0 is less than or equal to e to the negative x squared is less than or equal to 1 over x squared. We know that the integral from 1 to infinity of 1 over x squared dx converges. And so that tells us then that the integral from 1 to infinity of e to the negative x squared dx also converges. On another note, or another example, let's go ahead and verify whether the following integral converges or diverges. Or in this interval is the integral from 2 to infinity of 1 over the cubed root of x squared minus x dx. So just a quick note. The cubed root of x squared minus x is going to be less than the cubed root of x squared as long as x is greater than 1. Actually, it's just as long as x is greater than 0, we have this, but we'll go with x greater than 1. And so what we get is, cubed root of x squared minus x is less than the cubed root of x squared for x greater than 1. We could do x greater than 2 as well. So we have, therefore, 1 over the cubed root of x squared minus x should be greater than 1 over the cubed root of x squared. Since we have, and then of course that is greater than 0 on the interval from 2 to infinity, which is what our integral is over. We know that the integral from 2 to infinity of 1 over the cubed root of x squared dx. This is the same thing as the integral from 2 to infinity of 1 over x to the 2/3 dx. We know that this diverges. And so that means that the integral from 2 to infinity of 1 over the cubed root of x squared minus x dx also diverges. So this is a useful trick we can use for comparing two integrals. Again, if we want to prove divergence, we have to find a function beneath it that also diverges. If we want to prove convergence, we have to find a function above it that converges. In summary, to prove convergence, find a function above that converges. To prove divergence, find a function below that diverges. So to prove divergence, find a function below that diverges. And again, the most useful is if we can find a 1 over x to the p, since we immediately know whether those converge or diverge. In the next video, we will learn one other possible test we can use for testing for convergence or divergence.